Hey, welcome back to Abstract Algebra. In this lecture, we're going to start our work in Chapter 4. In Section 4.1, we're going to get introduced to a new algebraic object called a ring. And you probably have already noticed in our work in group theory or your work in previous mathematics courses that lots of sets have more than one binary operation. Like say the set of integers, for example, right? We can add integers and we know that the integers form an abelian group under addition. The identity is 0. Can also multiply integers. They don't form a group, but you can still multiply two integers together and get an integer, and that multiplication distributes over the addition. There's not necessarily a multiplicative inverse for every element, but it has two operations, and there's lots of sets that have two operations. So this notion that we're going to study now, this is called a ring, and it's exactly the mathematical object that turns out to kind of characterize things, or describe, not characterize, describe structures like the integers and so on, sets with more than one operation. So you can see the goals of this lecture there in front of you. I want to give you a definition of a ring, and then I want to discuss various types of rings, properties that rings may or may not have, and give a lot of examples. I won't be proving axiomatically that lots of these things are rings. I'm going to just be kind of mentioning the stuff that you need to think about, and I'm hoping you'll grab one or two of these examples and set about proving it's a ring yourself. This lecture is going to introduce a lot of terminology because we're already kind of experienced with what it means to study some algebraic structure like a group. So I'm going to go kind of fast in this. I tried to, in writing out the skeleton of the notes, I wrote technical terms in blue. You can see the first one there on the screen where I wrote a ring R. So I kind of made them a little bold and in blue. So I'm going to be defining all those terms as we go through the lecture, but I'm not going to bullet them out and define them like you would see in a textbook where it's going to say definition and then something careful. So if I were you, I would set about doing that yourself. I would kind of set yourself the following task: make a vocabulary flashword for every term that you see in blue in this lecture, and make sure that you have those definitions down, because it's the language with which we're going to describe our work in the next couple of weeks. So it's good to get it down early. Okay, so let's get going here. Let's just give the main definition. Herstein kind of strings this out into a bunch of little axioms. I'm actually kind of surprised because he's not really taking advantage of the work we've done in the first three chapters of the book. So the thing I'm defining is equivalent to what Herstein does, and maybe I can even try to open my Herstein as we're talking here, and I'll fill in what he calls these things. If you look in his chapter 4, when he defines ring, you're going to see a lot longer list of things than what I'm listing here, but it's because I'm taking advantage of our previous work. Okay, so let's look at this definition. What's a ring? A ring, it says, is a set together with two binary operations. And I'm going to just denote them with the addition symbol and the multiplication symbol, but you guys know that those binary operations might mean anything. They're sort of abstract. Two binary operations, and we'll just call them generically plus and times. And then here are the axioms. So the first ring axiom, R1, I'm calling it, is that under this operation of addition, the set needs to be an abelian group. All right. So that comes with a lot of baggage. That means that this addition is an operation. It's a commutative operation. There's an identity. We'll denote the additive identity by 0, like we always do. Every element has an inverse. We'll denote additive inverses with a minus sign. We always do. So Herstein, in his definition, he calls those things properties A through E. So this one thing in Herstein, he lists as 5 different properties because he's just recapitulating what it means to be an abelian group. All right, so I'm just throwing that into a single axiom. His second two things, F and G, I'm rolling into 1, that we have a binary operation and that binary operation is associative. Okay, so there's one of our blue terms. An associative operation is one that satisfies that grouping law. So Herstein throws these two things into his F and his G. Those are his next two, and then he has one more. His H is my R3 down here, and I'm calling those the distributive laws. So I quantified all this stuff once over here, but for any 3 elements, A, B, and C, the product of A with the sum of B and C is that familiar looking thing. And I'm not going to assume that the multiplication operation is commutative. So that's why I'm writing both, I just highlighted a left and now the right distributive law. So we axiomize that both of those things are true. Okay, so a set together with two binary operations that satisfy those three axioms, R1 through R3, is called a ring. And that's the object of our study. I'll certainly write it later on, but I think you should try to keep in mind that the integers form an excellent example to keep thinking about. The integers are an abelian group under addition. Integer multiplication is associative, and integer multiplication distributes over integer addition. So the integers form a ring. There are lots of other rings, but let's keep getting our vocab down here. Okay. So the multiplication operation may or may not have a multiplicative identity. If it does have a multiplicative identity, then we're going to denote it by the symbol 1. We won't denote it by E anymore in a ring. So the additive identity always denoted by 0. Multiplicative identity, if it has 1, is denoted by 1. And if the ring has a multiplicative identity, then we're going to say that the ring has unity. The multiplicative identity in a ring is called unity. Okay, so there's a different technical term for you. Unity is the name of the multiplicative identity in ring theory. A ring may or may not have unity. The example that I'm just still speaking out loud, the integers is a ring with unity. Here's just a little note. There is one ring, you can take the set with one element in it, that call that element 0 and define 0 plus 0 to be 0 and 0 times 0 to be 0, and it will satisfy all these axioms. It's called the trivial ring. It's absolutely non-interesting, but just as a technicality, I won't consider the trivial ring a ring with unity. Even though the 0 is acting like a multiplicative and additive identity. When we talk about rings with unity, we always mean that the multiplicative identity and the additive identity are different. All right, so the trivial ring doesn't have unity. Maybe I'll assign you an exercise. It's not that hard to prove that if you have a ring in which the multiplicative and additive identity are equal, then the ring has to be trivial. So that R equals 0 would be the only such ring, but we're just going to throw it out. Okay. In a ring, the additive group, the additives operation plus has to be abelian. R has to be an abelian group under addition, but the multiplication operation doesn't have to be commutative. So we call the ring commutative if the multiplication operation is. Okay. So if you have a ring in which it's true that the multiplication operation is commutative, AB is BA for every A and B, then we'll call it a commutative ring. A ring may or may not be commutative because we don't insist that the multiplication be commutative. All right, integers are our kind of one and only example that we're still just speaking out loud. It's a commutative ring. The integers are a commutative ring because multiplication of integers doesn't require, or it doesn't depend on the order. All right, if I'm going too fast, pause, take a breath. I just want to get this vocab out there. We can talk about it in class and do some more examples in class, but let's just get it out there so that you know what you're responsible for and this video doesn't get too long. So just like with unity, an element of a ring may or may not have a multiplicative inverse. Yeah, some do, some don't. So if you take an element in a ring, call it A, if it has a multiplicative inverse, let me remind you what that means. That means that there would be some other element B that you could multiply it by to get 1. And we would only speak of multiplicative inverses in rings with unity. Yeah, because if you don't have unity, then it doesn't even make sense to have a multiplicative inverse. The product has to work in both ways. We'll use the same kind of notation. If an element has a multiplicative inverse, we'll write it as a to the negative 1. And elements in rings that have multiplicative inverses are called units. Okay, so there's a new technical term for you. A unit is an element of a ring with unity that has a multiplicative inverse. It's called a unit. All right, a little bit more vocabulary. If somebody's talking about a division ring is a ring with unity where every non-zero element is a unit. All right, so everything except the 0 element has a multiplicative inverse. The 0 element never will. And a commutative division ring is called a field. Maybe you've heard that word in linear algebra. So a commutative division ring, I'm kind of packing that in. What is a commutative division ring? It's a ring with unity where the multiplication operation is commutative and every non-zero element has a multiplicative inverse. It's called a field. Okay, let's look at some examples. Let's finally write some down. We need some. The first one I wrote down here is the one I've been talking about out loud, the integers. The integers are a commutative ring. The multiplication operation is commutative, and certainly there's a multiplicative identity. It's 1. And I have a question for you here. Which integers are units? Which integers have multiplicative inverses? You can stop this because I'm going to say the answer, but think about it. Stop it and think about it. Which integers could you multiply by other integers and get the identity? It turns out that only plus and minus 1. The integers have exactly 2 invertible elements when you're talking about inversion with respect to multiplication, 1 and minus 1. Any other integer doesn't have a multiplicative inverse. Cool. How about the rational numbers? The rational numbers certainly have a multiplication and an operation, or a multiplication and addition. They're an abelian group under addition. Multiplication is commutative. There's a 1. The rational numbers form a ring. In a very natural way. I'm not checking all the axioms. Again, I'm leaving it to you. The distributive laws, these are properties that we know hold. Yeah, so the multiplication and addition of rational numbers. When you add 2 rational numbers or multiply 2 rational numbers, you get a rational number. They're a ring. Which rational numbers are units? Yeah, 0 is not. 0 is never a unit in any ring because 0 times something can't be 1. I'll prove that to you in the properties of rings lecture a couple days down the road. 0 is not a unit, but if you take a non-zero rational number, well, if it's a non-zero rational number, then A and B are not 0. Yeah, so B over A is also a rational number, and B over A is certainly A over B's inverse. So every non-zero element of the rational numbers is a unit. The rational numbers are a field. Rational numbers are a commutative ring with unity in which every non-zero element is a unit. Notice another way to say that. I kind of ran out of room here. Sorry, I'm squeezing this in, but the non-zero rational numbers then is a group. This is going to be one of your exercises, but the set of non-zero elements in any field forms a group under multiplication. Yeah, so that's kind of why we've had these 2 things, Q under addition and Q prime under multiplication, and we kind of always were thinking of them as different groups. Well, they're just the additive and multiplicative structure of the field of the rational numbers. Yeah, kind of been hiding that structure from you this whole semester. So same thing, we won't make long work of it. We can talk about it in class, but the real numbers and the complex number, they're fields. They're commutative rings with unity, and every non-zero element of them has a multiplicative inverse. Yeah, you can multiplicatively invert any non-zero real number, any non-zero complex number. Cool. The next example, I'm going to write some stuff without claim here, or without proof, rather. I'm going to kind of prove it in the next lecture, the one that corresponds to Tuesday. But I want to look at a finite group, Z6. We know Z6 is an abelian group under addition mod 6. Here I'm writing the brackets just to emphasize again the equivalence classes. But so addition mod 6 is a well-defined operation. Well, I claim that multiplication mod 6 is also well-defined. That's what I'm not proving here today. I'll prove it to you in the next video lecture. But just take it for granted for a second. I promise I'm a trustworthy guy, that the operation of multiplying 2 equivalence classes together by multiplying their representatives and looking at what class that in, that's also well-defined. And you can check, assuming that that's well-defined, this is an excellent exercise for you, that the ring axioms are all going to hold. Z6 is an abelian group. You can check that this multiplication is associative. It's done in terms of the integer multiplication, which is associative. It's a ring with unity. What would the unity element be? Can you pause at me and tell me? It would be the equivalence class containing 1. That would be the unity element in Z6. Yeah, when you multiply by 1, you don't change it. So just to get you used to this multiplication, like if I took, say, 2 and 5, those are elements of Z6. I multiply them together. Well, you might be expecting me to write 10, but I'm writing its equivalence class with integers between 0 and 5. So 2 times 5 is 4 in this ring. Likewise, 2 times 3, well, you could write 6, but that's 0. 2 times 3 is 0 in this ring. And that actually kind of is an interesting phenomenon because 2 is not 0 in Z6, and neither is 3. So this is actually kind of a peculiarity, yeah? Because in lots of things like these fields, real numbers, complex numbers, you can't multiply two non-zero elements together and get 0. In fact, all of the math you've learned about solving polynomial equations and so on, it all relies on that fact, that you can't multiply two non-zero numbers together and get 0, but you can if the numbers are, by number, you mean elements of Z6. All right, I can multiply two non-zero elements of Z6 together and get 0. Maybe you linear algebra veterans are thinking of another place where you know that happens. Okay, new vocab. We're going to call such things zero divisors. A zero divisor in a ring is a non-zero element for which there exists some other non-zero element, but their product is 0. So in my example up here, if you want to use some terminology, 2 and 3 in Z6 are zero divisors. Zero divisor means that you're not 0, but there's some other non-zero element that can multiply by you to get 0. Okay, a commutative ring with unity. Your author doesn't require them to have unity, but we will. So a commutative ring with unity is called an integral domain if it doesn't have any zero divisors, right? These familiar rings, Z, Q, R, C, they're all integral domains. They're all commutative rings with unity, and you can't multiply non-zero elements of those things to get 0. Z6 is not an integral domain. Yeah, it has zero divisors. Bracket 2, bracket 3. Those are zero divisors. Let's look at a non-commutative example. M2R, you remember it? It's 2 by 2 matrices with real number entries. M2R. I didn't write it in these notes. I can write it down here. M2R is the set of things that look like A, B, C, D, 2 by 2 matrix. All 4 numbers, A, B, C, and D, are real. And you have matrix addition. You have matrix multiplication. Product of two 2 by 2 matrices is a 2 by 2 matrix. Under addition, we know that this thing is an abelian group. I'm going to leave it to you to check the axioms, but yeah, it's a ring. The matrix multiplication is associative, distributes over addition. It's a ring with unity. The identity matrix, 1, 0, 0, 1, is the unity element. But it's a non-commutative ring. I'm relying on your linear algebra experience that given 2 matrices, it's not necessarily the case that their product in either order is equal. Oh, sorry, I already wrote that it has unity up here, the identity matrix. Oh, and by the way, sometimes when I write matrices, I use square brackets, sometimes round brackets. I don't mean anything different by that. That's just laziness. Looks like I was in a square mood today. I was in a round mood when I wrote those. Yeah, good. A couple of questions here. What are the units? What are the units in M2? You might say, well, how do I know what the units are? But let me just ask you in another way. I'm asking you, what do we call the set of 2 by 2 matrices that have multiplicative inverses? The set of 2 by 2 matrices that are invertible. Oh, we have a name for that. It's just this group. Yeah. The set of units in a ring is always a group. We're going to prove that. We're going to prove that. But yeah, GL2, it's just the group of units in the matrix ring. The invertible unit, the invertible elements. Cool. I took up my room to answer this last question, so I have to kind of, well, I can move it, I guess. There, that's pretty magic. Does it have zero divisors? Pause, ask yourself, can you multiply 2 non-zero matrices together and get 0? If you've had your linear algebra class, I think you would have seen that the answer to that question is yes. These are certainly not the only examples, but I think this is an example. Neither one of the matrices I just wrote down is 0. Yeah, because it doesn't have all 0 entries. But if you multiply these two matrices, right, if you do the row dot column, well, that column is 0, so this whole row will be 0. And then when you do row dot column, this whole row is 0, so both columns will be 0. So you can check that out. Yeah, that ring has 0 divisors. Okay, so I will just zip back to the top as I close out here. What did I try to do? I tried to give you a definition of a ring. I gave you lots of types of rings, lots of technical terms that were all written in blue. You're going to make some vocabulary flashcards for those. Ask me about any definitions you need clarity on. And then we looked at lots of examples, most of which were commutative. The matrix ring was the only one that wasn't. Next time, just to let you know what I want to do, I want to try to prove that multiplication is well defined in those finite rings Z sub n. We only looked at Z6 here, and then some various stuff about that. Okay, thanks for listening.